The last topic in the chapter is optical resolution. So if I have two stars that are 3.3 times 10 to the minus 6 radians apart, so it's a pretty small angular separation. So let me draw a little picture. So there's my two stars. So what I'm saying is that if I look at the angle between them, wherever my telescope is, I get 3.3 times 10 to the minus 6 radians. I want to know what diameter of my telescope objective is necessary to just resolve those two stars using light with a wavelength of 650 nanometers. Right, so what does this even mean? Well, our equation, the Rayleigh criterion, is that the minimum angle between them at which I can resolve them is 1.22 times the wavelength divided by the diameter of the telescope objective or microscope objective, depending on what you're looking at. And so I'm told my angle, I'm told my wavelength, I want to find d. So just rearrange it. D is equal to 1.22 lambda over theta. So I've got 1.22. My wavelength, I got to put everything into meters. So 6.50 times 10 to the minus 7 meters is 650 nanometers. Divided by my theta, 3.3 times 10 to the minus 6 radians. And I get a diameter of 0.24 meters. So that's a diameter of something like 10 inches. Right, so that's a pretty reasonable sized telescope. Right, so it's not one that you'd probably keep in your bedroom window, but it might be one that a reasonable small observatory would have. Okay, so let's do something that's a little bit closer to home. We've got two light bulbs, so say they're the light bulbs on your ceiling, and they're 1 meter apart. I want to know how far away can I go away from those two light bulbs and still see that it's two light bulbs instead of one light bulb. So I've got my two light bulbs, they're 1 meter apart. And I've got a little telescope, and my telescope has a 4 centimeter, so D is 4.0 centimeters. And of course, I got to put it to meters, 0.04 meter diameter objective. And I'm going to assume that the wavelength of the light is 600 nanometers. So that's 6 times 10 to the minus 7 meters. All right. And I want to know how far away can I go. So let me draw a little picture. So I want to know how far can I go. So what's my distance here, R, that I can go and still see them. So if I want to get my R, what I know is that these two guys are 1 meter apart. And so remember, I don't know when you would have learned this, high school probably, S equals theta R. The S, the distance between them, is 1 meter. Theta is the angle between them, and R is how far away I am. So I'm trying to find R. I know my S, so I need to find theta before I can find it. So how can I find theta? Well, I've got that equation, right? Rayleigh's criterion, 1.22 lambda over D, and I know my lambda and I know my D, so I'll just plug and chug. So I've got my lambda, 6 times 10 to the minus 7. My D is 0.04, and when I put that into my calculator, I get a very small number, 1.83 times 10 to the minus 5. So now I know my theta, so I'm just going to find, so I've got 1 is equal to theta times R, so R is equal to 1 over theta. So I've got 1 over 1.83 times 10 to the minus 5. And so if I'm dividing by a very small number, I'm going to get a big number, 54,645 meters. How big is that? That's about 55 kilometers. So I can be really far away. And if I've got this telescope that's got a 4 centimeter, that's about 1.5 inch diameter lens on it, I should be able to see two light bulbs that are 1 meter apart.